Okay, so this is the next series in the series of my attempt to tell you everything I know about MATLAB for Chapter 10. Oh, shut up, cat. Oh, cat drives me nuts. Oh, sorry. Anyway, so this one is dealing with matrix algebra. So this is kind of a reward for getting through chapters 8 and 9. Oh, I hope I don't lose my voice through this. Where'd my coaster go? Somebody stole my coaster. Where are my coasters? Okay, I'll just put it on the computer. That's not going to hurt the computer if it gets all moisty, right? Sorry. So yeah, I'm still feeling the effects of COVID. I still have issues with concentrating. So if I get too far off tangent, just rattle my chain, say, "Hey, stupid, get back on topics. We want to go to bed early tonight." So chapter 10. You can't see it yet because I haven't started displaying it. I knew that. I'm going to go over here and hit start from beginning. Okay, now you can see it, right?
Yes, sir.
Okay, I'm going to get rid of all these little pop-up windows that were over here and move them down so they're not in the video, because people don't want to see all this stuff in the video. Okay, so this is chapter 10 from the 6th edition, Holly Moore. Holly has been in contact with me the last few days. She has all the PowerPoints done for the 6th edition, so now she's going through and working on finishing up the grader problems. So I'm hoping she started on chapter 10. I'm not sure. If not, I'll do what I can to get chapter 10 out, but I also have to get the exam out this week. So anyway, hey, I said go to the next slide. There we go. So the learning objectives for objectives. The learning thing is up there that says after reading this chapter, you should be able to perform the basic operations of matrix algebra. It's a little bit different than what we've been doing with the element algebra, element operations. So we'll cover that in just a second. You should be able to explain the difference between an array operation and matrix. See, it looks like I just told you right there, 10.2. Tell the difference between the array operations and matrix operations. Use dot product MATLAB to solve some engineering problems, and also matrix multiplication. And then probably the most important part of this chapter is solving systems of linear equations. And there are 3 built-in MATLAB techniques, and one of them I've had students use before in the past, and because we didn't teach it, I always told them that I wouldn't accept it. And so this now in the 6th edition, it's there. So I guess I can't do that anymore. Unless now, just beware. If I give you a test and it says use the inverse method and left division to solve these linear equations, that's what I want you to do. Don't be using the reverse row echelon function, because that's not what I asked for. Anyway, and then use some special matrices to demonstrate matrix algebra concepts. So one of those special matrices you've already seen, I think. Yeah, you have, because we did it before. I think back in chapter 3 or something like that. Anyway, so that's the objective. So our introduction today is an array is usually a grouping of information, be it character data, symbolic data, names, numbers. It could be just about anything. This array terminology has been introduced in the 6th edition. Prior to the 6th edition, we called everything a matrix. But technically, a matrix is a 2-dimensional numeric array used in linear algebra. And I like this. All matrices are arrays, but not all arrays are matrices. Okay, that's okay. Yeah, I'll keep my opinion. Anyway, so in this chapter, we're just going to assume that all of our arrays are matrices. Yeah. Okay. We'll move on. So matrix algebra is used extensively in engineering this first introduced in if you remember way back when, for me that's a long ways to go back to my college algebra course. I think I started my degree for mechanical engineering in 96. I think it was 96 is when I started, because it was before my daughter was born. She was born in 97. So that's a long ways for me to. I don't even remember what I did yesterday. You want me to remember back to 96? I can't do that. So anyway, so you'll start using these regularly when you get into some of your higher engineering courses, statics, dynamics, especially if you go into finite element analysis. There's a lot of array matrix multiplication and stuff going on in that course, numerical methods. And then also for you guys, you'll use it quite a bit in your electrical engineering courses. And I'm going to silence this thing so it quits making noise. Stop it. Okay. So anyway, we're going. So in previous chapters, all our calculations were in using arrays. That was with a dot multiply, dot divide, dot raised. That made it an element by element calculation for the arrays. In this chapter, we're going to introduce matrix algebra, where you're doing things in a matrix form, not element. And this also, for those of you who've already read the textbook, goes into a little bit about matrix architecture and how the multiplication and everything is derived. Okay, so transpose. We've been using transpose since probably the second chapter. Basically, what this does is it inverts the matrix about the diagonal. So about this line right here. Oh, well, you can't see it. I don't know if you can you see my mouse? I'm hoping you can see my mouse. Anyway, it transposes it. It makes the columns vector, columns rows, and the rows columns. Man, it's going to be a long hour. About this angle here, or this diagonal. So if you notice that this row is now this column and this column is now that row. That's what transpose does. And in mathematical textbooks, it's usually indicated with a superscript T as thus. And that's the way she indicates it most, I think, throughout the textbook when writing something like this. But obviously the code for MATLAB is with a single quotation mark. So here we go. It transposes the numbers. Let's see. I didn't lie to you. Oh, I'm not going to go backwards on me. So it goes the rows to columns and columns to rows. Okay. So it uses a single quotation mark, which does that all for you. And one of the things we use it for mostly right now has been changing a row vector to a column vector, just to make it easier to read on the screen. Or if you're creating tables, or you go from columns to rows if you're setting up variables for the fprintf, because you got to have one row for each placeholder in the fprintf statement. So transpose is a pretty common function that we use. When you use a transpose on complex numbers, you get the complex conjugate. In the other formations, so this row of imaginary numbers gets complex conjugate in a column vector form. Say, ooh, that's cool. Yeah, he's losing it, man. He's losing it. Okay, so the dot product. This is one of the first basic matrix algebra functions that we use in this course. Is dot products, and basically what it does is it takes two vectors of the same size. They got to be the same size, 1 by 3, 1 by 3, 2. It even works in multiple rows and columns, but they got to be the same size. And it doesn't matter if they're both rows, both columns, or one of each. It will still calculate the dot product, but they've got to be the same size. And basically what it is it's this one times this one plus this one times that one plus this one times that one. And then it adds them all up to get the total. So here is the drawn out way to do the dot product, and here it is with just a simple single line dot product. So that's what a dot product does. And mathematically, it's represented as the sum of from 1 to the number of elements of A times B. So you multiply them, add them together, and that gives you the dot product. And it doesn't matter the input either. You can do A dot B or B dot A. You'll get the same answer. But that's one of the very few instances in matrix algebra where that condition holds true. Another one is coming up here in just a minute. So matrix multiplication is it's basically the multiplication in which each element is a dot product. And we'll show you that here in just a second. So the operator is just the asterisk between the matrices, and again it can be expressed mathematically as a sum from k1 to n of A times B of A row A so this I think that comes up in a minute here too, but basically the size of your matrices is critical. When you put the sizes together, the number of columns needs to equal the number of rows in the second one, and then your final product will be this many rows and that many columns. Pretty cool, huh? Say, yeah, man, that's just blows my mind. Okay, so more puts in the values and the result are found by taking a dot product of each row in matrix A with each column in matrix B. And we'll show you that here in just a second. So each column in C is a dot product from the row and column. So you take this row and dot it to this column, that gives you that value. This row dotted with this column gives you that value. This row dotted with that column gives you that. And then the same thing with the bottom. This one dotted that one, this one dotted this one dotted that one, and this is your resultant vector matrix array. This is your answer. I gotta forget something old to learn something new. So here's just it's going through and showing you the hard way of taking row 1, row B, and multiplying them together, and so it pulls them out, and then the second, and then doing a dot product on the two shows you that those are the same. Okay, any questions? No? Okay, cool. See here I told you. So because matrix multiplication is a series of dot products, the number of columns of A must equal the number of rows in B. So that's very, very important that these two numbers are exactly the same. Because if they're not, then you can't do a dot product of this one to that one. If matrix A is n by n, the B must be n by p, and the result will be an n by p. So this is what I remember from back in. I do remember some of my linear algebra, college algebra, that to visualize whether they work or not, you write them side by side, and the two center ones have got to be the same number. They must match. And I did tell Holly that this text box is not red like the rest of them's in her PowerPoints. There's another one coming up here in a couple slides too. So matrix multiplication in general is not commutative. It means that A times B is not equal to B times A. They're not the same, because if you have a 3 by 4 and a 4 by 3, well, that would work. A 4 by 2, the center numbers would work, but if you flipped them around the other way, then they wouldn't work. So it's not, but there is, I don't know if this one goes in to say, there is one case where you can, and that's if you're multiplying square matrices. If they're the same size, a 3 times 3 by 3, they're both 3 by 3 or both 4 by 4, then it doesn't, order doesn't matter. You'll get a different answer, but you can, unless one of them is the identity matrix. If one of them is the identity matrix, then it doesn't matter direction. They'll equal the same. But if it's not the identity, you can multiply them no matter how you put them in, but you get a different answer both ways. And there's an example of that in the textbook. So, and here's another one that she didn't do the red around, and it fiddles with my OCD. It needs to be red. Okay, I'm not going to change it right now. I did tell her though that it's got to be red. Anyway, so square matrices, it's easy to make square matrices, like I just said, because they're the same. You can multiply. A times B will multiply, and B times A will multiply. But you notice they are completely different answers because you're crossing, you're doing dot product with this and this in one direction, and then in the other one you're doing dot product with this and this. So they are not the same answers, but you are able to multiply them together. Okay, if I'm going too fast, just tell me to slow down. Matrix powers, you can take a matrix and raise it to a power, any power you want, but there is one condition: it must be square. If it's not a square matrix, you can't do it. Again, it's like the numbers just don't line up right. So you've got to have a square matrix to raise it to any power, 2 power, 3 power, 4 power. Because if you got a 3 by 3 and you square it, you're going to end up with a resultant that's 3 by 3, and it'll just keep going and going and going. So yeah, cool. Inverse matrix. What does taking the inverse mean? Your basic mathematics, if you consider the inverse, like the inverse sine, it just means that you're going to undo the sine and find out what the angle was that gave you the resultant of the value which you're trying to take the inverse sine of. Same with the log value. But that's not what we're doing here. So here's a long drawn out explanation of, the inverse is 1 over a number and multiply it to get you back to 1. Multiplicative inverse is first discussed, and additive inverses such as minus A. So in the matrix, you need to multiply using matrix algebra to get the identity matrix. And the identity matrix is a matrix where 1 is the main diagonals are all 1s and everything else is 0s. That's a matrix identity, or an identity matrix. Oh man, I need to get some scotch in this glass. Oh, sorry. It's just water. Find the inverse matrix you use, and this one's very important. Okay, so Boyd, I don't know if you were here last night on the review, but some idiot who was doing the review for the exam tried to take the inverse of a function by spelling out the word inverse, I-N-V-E-R-S-E, and it wouldn't work. It kept saying, okay, you need a toolbox that's called the mapping toolbox or the wavelet toolbox in order for that function to fit. And wait a minute, I don't need those. Those have absolutely nothing to do with linear algebra. And then it dawned on me it dawned on the idiot that was doing the presentation, because it wasn't me. I wouldn't be that. Okay, I'll be nice. If you spell out the entire word I-N-V-E-R-S-E, it works great if you're in Excel, but not in MATLAB. MATLAB is just INV. Okay, that's something I'll probably remember for my dying day now, because I did that, and I did it in front of students that I'm trying to convince that I know what I'm talking about, and I hung my head in shame last night and crawled in bed and what did I do? I was playing a slot machine until 1 o'clock in the morning. Anyway, so you can do the inverse, or you can raise the matrix to a -1 power. Both of them will give you the same results. If you see here, A to -1 and A inverse gives you the exact same. So if you're like me and you forget the 3 little letters INV, then just raise it to a -1. It works just as great. Just make sure that when you raise it, you got that inside of parentheses. So the inverse operation is commutative. It means that A times its inverse is the same as the inverse times A. This is one of those rare cases I was telling you about. The order does not matter here, because both directions will give you the same answer. and then here, these little negative zeros is all just due to rounding errors. Which, if you read the textbook, says that they are saying that if you're doing linear system of linear equations, this is not the best method to use. You'd be better off with the left divide or the reverse row echelon function. Those are more accurate than the inverse, which kind of makes sense, because if you're adding more processes to I just learned how to fuck yesterday, to the solution, then there's a greater chance of something throwing in a wrench into the works. Determinants. Determinants are used in linear algebra and related to the matrix inverse. If the determinant of a matrix is 0, then it does not have an inverse, and it's declared as singular. So the built-in MATLAB function for finding a determinant is det. Now, if you look in the textbook, it'll explain to you what the determinant is. It's like this one times that one minus this one times that one, and all added together, or some silly thing like that. Yeah. Hello? Is there anybody in there? Just not if you can hear me. Is there anyone at home? Oh, determinants. Okay, so we know matrices with determinant 0 do not have inverses, and therefore there's no solution when you're doing a system of linear equations. However, it is possible if poorly scaled or close to matrices return determinants that are very close to 0, and it'll still give you a somewhat of an inverse, but look how small those numbers are. That's times 10 to the 16th. Or large, actually. Yeah, I mean, that's very, very, very close to 0. So okay. Any questions on that? No, he just muddled his way through. Okay. Cross product. I remember using cross product a lot in dynamics. And I think a little bit in physics. Basically, vector. It's sometimes called a vector product. The result from dot product is scalar, whereas a cross product is a vector. It's basically taking two vectors and multiplying them together to give you a new direction of the resultant vector of the two vectors, and it gives you magnitude and angle and all that other good stuff. And I like this word. I use this word quite a bit, and people are, what the heck is orthogonal? Basically, orthogonal is just perpendicular to a plane. Is always at right angles to the plane defined by the two intersecting vector input vectors. A property called orthogonality. That's like prestidigitation. I like prestidigitation too. My high school a calculus teacher, whenever you asked him, how did you do that? And he says, prestidigitation. So that term's been with me for a long time. And if you don't know what prestidigitation is, it's what a prestidigitator does. Okay, he's rambling again. Somebody's slapping, tell him to get back on. Vector notation. So here are two vectors. So this is the magnitude in the x direction. This is the magnitude in the y direction. This is magnitude in the z directions, and these just indicate that they are vectors. Let's see. See, I told you. See, ax, ay, bz represents magnitude of the vector and the directions. The symbols I, j, k represent the vector unit vectors. So the cross product of A cross B is defined as, and I'm not going to read all that up because I guarantee I'm going to screw up some of those. But anyway, so it's It's these technically it's the if this is the x, it's going to be the y z's. This is the y, so it's be your x z's, and this would be your z's, be your x y's, and that'll give you the magnitude, and then you can calculate out the direction. So each vector must have 3 elements, since they represent vector components in 3 space. And if it doesn't have one, a value of 0 should be used. So oh, sorry, a little leftover. So use the following code for cross product. So this would be your XYZ, so across A, this is your resultant vector, which is -3 in the X plus 6 in the Y, -3 in the Z. Ooh. And then that's just like other matrix mathematics, they are not commutative. So cross AB is not the same as B cross A, because you get a different signage. So I guess that would be the anti-orthogonal. Oh, that's not a good word. Okay, so I don't know why we're doing matrix entity again. We already did it once about 5-10 slides ago, but here it is again, just to make a encore presentation. The identity matrix is one with ones on the diagonal and zeros everywhere else. And you can create this by a function called I, EYI, and if you put in a scalar value, it's like 6, it'll build you a 6 by 6. If you do a two values, like if you did a 3 and a 4, it would give you 3 rows and 4 columns, and it would just have basically, I knew I was going to do that. The last column would be all zeros, so the diagonal will go down until it hits the bottom row, and then all the rest of them will be trailing zeros. I know that's because I tried it before the lecture because I wanted to make sure, but I remember reading that in the book, but it wasn't in the PowerPoint. So okay, so systems of linear equations. One of the most useful, important uses is solving linear equations. So there are 3 techniques to use in MATLAB for solving these system equations, which is the inverse technique. We'll cover that in just a minute. It'll explain it. There's left division, which implements the Gaussian elimination, which means basically you take 2 equations and you get down to where you eliminated everything to where you got one value left over, so you take that and then it's a long drawn out process. You probably remember doing that. And then there's the reverse row echelon function, which implements a Gauss-Jordan elimination technique. These two here are almost identical they are 100% identical in setup. Just the implementation differs. This one here is different from those two, and I don't think the PowerPoint showed the reverse row echelon function. So when we get done, I'll show a little example of it. So in each of these have advantages and disadvantages. So here's a matrix with 3 equations with 3 unknowns, x, y, z, with the resultant vector, with the results here. So we can write this as system equations by pulling out the coefficients from all the variables. And if there's a minus there, that makes it a minus to the -1, and if it's missing, you put in a 0. And then the results should be put in a column vector over here, B. I know Aiden, last night I put that as R. Sorry, it's trying to teach an old dog new tricks. So now it's called B, and X is basically just your variables, X, Y, and Z. And then we can write this down as A times X is equal to B. Okay. So from that, the most is to solve the question is use the inverse. So because the inverse times A is equal to the identity matrix, which is all ones. So if we put a 1 here in form of the inverse and the A vector matrix times X is equal to the inverse times B vector. Well, this is 1, so that leaves you with X is equal to the inverse of the A divided by B. And definitely order matters. Oh, nice, Holly. So I hope she doesn't ever watch these, because she'll, yeah, I don't know why she would. Okay, so yeah, order matters, because if you do B times the inverse A, it won't work. It'll give you garbage. So here's an example. A is equal to 2 minus 1. Basically, I think this is the same vector matrix that was over here, right? Was it? Yeah, so this system equation, so we come in here, we put it into MATLAB, we got the coefficient vector matrix, the resultant matrix, and then we do inverse A times B, gives us minus 2, 5, minus 6. And just to show that you don't have to use the inverse, you can use raised to a negative 1, gives you the same results. Is that cool or what? Say, yeah, that's cool, man. Okay, so easy to understand but prone to error, because like say doing the inverse introduces rounding off errors, and then you're going to multiply again, which creates more errors. So right here, this textbook is now saying that inverse matrix inverse of solved linear equation should be avoided. So, you know, and there are other ways to do it. Although I don't think there's other, I don't know, I don't remember. It's been a long time since I've done any Excel. I haven't had any Excel students. They all leave me. Oh, MATLAB, not Excel. So yeah, so here's the left division. So a better technique for solving these equations, system equations, is using the left divide, which is a Gaussian elimination technique. Is the approach in eliminating variables until only one exists, and then substituting back to all the unknowns are undetermined. I remember doing that in college algebra, and yeah, it's fun. So the left divide operator is not the regular divide. This one is the one that goes backwards. On my computer, it's the one right above the enter key. Okay, make sure that it's going this way. It's going backwards, because if you do this one, it'll still produce an output, but it's not right. It's got to go this way, not this way, this way. Okay, I hope you can see my mouse going backwards and forwards. Okay, so I think I've got that drilled in. It's this way. Okay, so here we go. Same problem that we just did with the inverse method, and it's just a matter of A left divide B, which gives us the exact same output. So yeah, that's cool. And then yeah, okay, I'll do the reverse row echelon function after I get done with this. Okay, so overdefined and underdefined systems, MATLAB is also capable of solving these problems if you've got too many equations, and if you got more equations than unknowns, and also too many unknowns and not enough equations. However, just be aware, at least with the too many unknowns and not enough equations, the accuracy is greatly diminished because it just has to make assumptions on some things. So here's an example. Left division can be done 3. So this one is 3 and 3 unknowns, 3 equations. But here we have now, we introduce another equation of 2x minus 4 minus 7 is equal to minus 27. And it can still solve that and obtain the same results. So, well, not saying, well, it gave us results because the equations are consistent. However, if we introduce an error into the system, inconsistent is usually coefficients and resultant vectors data gathering. The commonly occurs when the coefficients of the result or the results are the results of data gathering operations. So MATLAB will then use the least square approach to solve the equations. And this is described later in the chapter, which for all my 1020 students, if you want to learn that, you'll have to take it upon yourself, because you're not required to do anymore after this chapter. Ooh, and I got yelled at for that too, but we won't talk about that. So anyway, so here we got the same first four equations, but the fourth one changed that to a minus 28 instead. And so it calculated it, and the equations before came out 1, 2, 3. This time there's just a little bit of difference in there. And so if we go back through and multiply the resultants by the A variables, coefficients, we get this with the calculations, and so there's a slight difference in values. Okay, but I don't know. Okay. And then undefined systems, if you don't have enough equations for your unknowns, it basically will consider it as two equations with three unknowns, and it'll add zeros in for variables until they become equal. So it's an iterative process, and it just goes in and out until it reduces it to two equations and two unknowns, and then it solves it. Fun, huh? Oh, hey, it does have the rotor. Okay, cool. And I went through this PowerPoint before setting up tonight, so, and I can't even remember that this was in here today. So this is the reduced row echelon function. It's a technique that requires changing. It's iterating until a solution converges. So it may be more efficient for larger problems in the Gaussian elimination. So it's the RE or RRF. Come on, you can see letters and you can say them at the same time. RREF, reduced row echelon function. And so what you got to do on this one is take the coefficient matrix and add the resultant as the last column in that vector, or not vector, matrix. So we took the coefficients of A and coefficients of B and put them all together into one matrix, and then call up the reduced or reverse row echelon function with a single input, and it calculates it and iterates it until it finally gets the identity matrix over here, and this is your solution. Pretty cool. Far out, right arm, out of state, and all that other good stuff. And then the X in the floating row is your answer. Okay, so I know you've been waiting patiently for this, but this is the special matrices that are listed in this textbook this time. These are supposed to be useful for testing numerical techniques. They serve in computational algorithms, or they are just interesting. I know when I get bored, I open up my MATLAB and I just start there and throw out matrices. Okay, be nice. So anyway, so some of them are cool. Pascal, and that's kind of cool. If you look on page 409 in your textbook, it shows you the output. So like here, it did a Pascal 4, and it's got first row and columns are all ones, and then the second row and column is 1 through 4, and then the third column is 1 through 6, and the last one is 1, 4, 10, 20. It's kind of cool. I don't know what I'd ever use it for, but it's kind of cool. Magic matrices, we've used that one before in the homework. It just makes a matrix where all the rows, columns, and the main diagonals all add up to the same value. And the Rosser creates a Rosser matrix used in an eigenvalue test matrix. And I don't know that it doesn't show. It just, yeah. I've never heard of that function. I've never seen it before in the book. It requires no input. So cool. cool. And then gallery function provides access to over 50 different test matrices, and the book says use help to determine which is right for your needs. Okay, so summary. Transpose, we've been using it. Now you know what it does. It transposes left rows to columns. Dot product is a summation of the product of the two vectors, and across matrix multiplication is just a whole bunch of dot products put together into a resolute. The multiplication is not commutative. You can't do AB does not equal BA. Raising a power is possible, matrix to power, but they must be square. Identity matrix times itself, or an inverse matrix times itself. I'll give you the identity matrix. Techniques for determining the inverse. Okay, yeah, you can do that. Determinant of 0 does not have an inverse. Cross give you for multiplying vectors, cross products. Yeah. System of linear equation is the inverse, left divide, and the reverse row echelon function. And then there's Pascal magic and gallery. Oh, and where's Rosser? She left Rosser out. Oh, he's so sad. Okay, so I've been blathering on for 41 minutes and 46 seconds. You guys got any questions? Or are you just ready to get away from me because I'm driving you absolutely batty?
I'm all good.
Did you get anything out of that, or was it